Hello everyone, this is our 8th educational based video. In this video we are going to learn about a topic SFD, BMD and AFD, that is shear force diagram, bending moment diagram and axial force diagram. Now this topic is important for the engineering students of branches like civil, mechanical, automobile and related branches. Also this topic is important for the other branches also for first year of engineering. Okay, and now before starting with the video, one thing we want to mention clearly that from the previous video we have started explaining what are the exact uses or real life applications of whatever topics we are studying. We are going to study in whatever the videos we post, so that applications or uses we will be explaining at the end of the video. So now let's start with this topic. Now this topic starts like I have divided this topic into different types of beams. So first is simply supported beam. Okay, now see, I have taken a beam of like 4 meter span, and at the center exactly 10 kilonewton load downwards is concentrated. Okay, and this is exactly at the center, so I have mentioned similarity over here. Okay, now this point is A and this point is B. First of all we will calculate support reactions. So summation Fy equal to 0. Now how to calculate support reactions we have also explained in one of our videos, so I'll give that link also, so you can go through that also. Now see, summation Fy equal to 0 we are doing, that is Ra upward, so positive, we are taking upward positive, then Rb upward, so positive, and this 10 kilonewton load is downward, so we are taking minus 10. So we will get an equation as Ra plus Rb equals to 10, equation number 1. Now we will take our next equilibrium condition, that is summation moment at A equal to 0. So this 10 going clockwise, we are taking clockwise positive, one may take clockwise negative and anti-clockwise positive also, so but here I am taking convention as clockwise positive. So summation moment at A I am taking 0, so 10 going clockwise, so positive, and the distance 4 divided by 2, that is 2 meter distance is this, so 10 into 2, then this Rb is going anti-clockwise, so minus Rb into the distance is 4 meters. Okay, so I'll get the answer of Rb as 5 kilonewton. So if I put this value over here in equation number 1, I'll get value of Ra as 5 kilonewton. Now we have to do shear force calculations. So see, you can see clearly this shear force at A is nothing but Ra. The value of Ra we have received as 5, so I'll just draw this vertical line for my shear force diagram. See, for shear force diagram we have to take, if I am going from left to right, we have to take upward positive, and units are obviously, if the forces are given in kilonewton, so the unit of whatever the diagram we are doing, it will be in kilonewton only. Okay, so it is 5 over here. Now in between from A, before reaching point C, there is no load, so it is a straight line. Now as soon as I reach this point C, I am getting this downward load of 10 kilonewton. So what we have to mention is shear force at C left is 5 kilonewton, and 5 minus this downward load, that is 10, that is minus 5, so you have to go down, that is minus 5. Now between C, before reaching point B, there is no load, so you have to draw a straight line, that is of 5, and as soon as we reach point B, we are getting this Rb of upward load, that is 5, so minus 5 plus 5 will get answer as 0. So this is nothing but our shear force diagram. Now to do bending moment diagram, or to draw bending moment diagram, what we have to do, we have to first do bending moment calculations. So always remember, if it is a simply supported beam, that is one end will be hinged and other end will be a roller support. So always the moments at the ends will be 0. So I have written bending moment at A equal to bending moment at B equal to 0. So you have to draw 0 0 over here. Then to find out bending moment at C, either I can see from this side or from this side. Now whenever I draw my bending moment diagram, see, I have mentioned bending moment diagram clockwise positive, and the unit, obviously the unit of moment is kilonewton dot meters. So this force is Ra going clockwise, so I am taking positive, that is 5 into the distance is 2, so 5 into 10, that is 10 kilonewton meter. So I have to just draw an inclined line, and then I have to again connect it here. So this is what about SFD and BMD of a simply supported beam. Okay, now see, second type of beam we are taking is cantilever beam. Now I have taken this cantilever beam of span 5 meters, and obviously it is cantilever, so one end will be fixed, other end will be free. Now here I have taken a UDL, that is uniformly distributed load, of 20 kilonewton per meter. Now this point is A and another point we, let's say, B. So this at point A, as it is a fixed support, so we have to take one unknown moment MA, then unknown shear force vertical VA, and horizontal force HA. But obviously as there is no horizontal load, so HA value will be 0. Okay, now first of all we will calculate the support reactions, that is summation Fy equal to 0. So we will take VA upward positive, so plus VA minus 20, that is UDL, so it is length, that is 5, and intensity is 20, so minus 20 into 5 equal to 0. So we will get VA equals to 100 kilonewton, upward arrow. Okay, now when we calculate summation moment at A equal to 0 and clockwise positive, what we are getting, this MA is anti-clockwise, so minus MA, as we are taking clockwise positive, then plus 20 into 5 into 5 by 2. So this UDL is 20, so like intensity is 20, so 20 into 5, that is a length, into length upon 2. The concept we have explained in our second last video. So into 5 by 2 equal to 0, and value we will get for MA as 250 kilonewton meters, and whatever value we have got is positive, so our assumed direction, that is anti-clockwise, is correct. So that is MA is anti-clockwise 250 kilonewton meter. Now to do to draw shear force diagram, first of all we have to do shear force calculations. So just remember, for a cantilever beam at end support, the shear force will be 0, and when we have to reach over here, what will be the value is nothing but value of shear force at A is nothing but 100. So 100 kilonewton, you have to draw this triangle, and I am taking shear force diagram. Upward force is positive and the unit is kilonewton. Now to draw bending moment diagram, so we have to do first bending moment calculations. So remember, at the end of a cantilever beam, moment will be always 0. So bending moment at B we are taking 0, and at A, see, we have got a moment MA, that is nothing but bending moment at A, which is 250, but it is anti-clockwise and we are taking clockwise positive, so it will go downward, the diagram. And remember, for a shear force diagram, if there is a UDL, you have to draw this curvature as parabolic in nature. So my style of drawing this parabolic nature is, I'll just draw this simply like a curve, and I'll just draw these lines and I'll just denote P. Some books, like many of the books, they will just draw a curve and they'll just indicate by a line and they'll write down parabolic or parabolic curve or parabolic shape. I'll just do this, like I'll just draw these lines and I'll mention P, so the examiner understands this is a parabolic curvature. Okay, now this is all about cantilever beam. Now our next type of beam is overhang beam. Okay, so I have taken this overhang beam wherein this, see, from A to B length is 5 meters, and I have taken a UDL. This is also a style of showing UDL, that is 8 kilonewton per meters. Then from B to C there is no load and the length is 2 meters. At point C we have an anti-clockwise moment of 10 kilonewton meters. Also we have an inclined load, that is inclined at 60 degree to the horizontal. We have a load of 20 kilonewton. Then from C to D there is no load, but the length is 3 meters. At point D there is a roller support, so also there is a moment of clockwise direction, that is the intensity is 4 kilonewton meters. Then at point E, this is the overhang, like this is the hanging support, hanging beam. So at this point, at 45 degree to the horizontal, we have a load of 12 kilonewton. So this overall beam length is 5 plus 2 7 plus 3 10 plus 3 13 meters. Okay, so obviously we will have the unknowns as VA. There is no there will be HA, because there is a inclined force also. So this is VA, HA unknown, like later on we will find it out. And also we have VD. So let's start with the calculations. So to do calculations, see, first of all we will do, see, I'll just put my mobile like this. Okay, wait. Yeah. So what we will do, we'll first take summation moment at a equal to 0. So when we take summation moment at a equal to 0, what do we have? See, we have this, first of all, UDL, that is intensity is 8 kilonewton per meters. So 8 into the length is 5 into 5 by 2. So that is what we have written, 8 into 5 into 5 by 2. Then this moment of 10 kilonewton meters going anti-clockwise. So we'll write down minus 10. Then this inclined load, see, we have resolved this inclined load as vertical 20 sine 60 and horizontal 20 cos 60. Also this load again 12 vertical sine 45 and horizontal 12 cos 45. Okay, so this vertical will be 20 sine 60, and as because this 20 sine 60 is going clockwise, so positive, and the length is 5 plus 2, that is 7 meters. So 20 sine 60 into 7, that is what we have. Then the next is this anti-clockwise moment, that is of 4 kilonewton meter, and for a moment there is no need of writing length, there will be no length, so plus 4 as it is going clockwise. Then this VD going anti-clockwise, so minus VD into the length is 5 plus 2, 7 plus 3, 10. So minus VD into 10 plus, see, this 12 sine 45 again going clockwise, and total length as we said 13 meters. So plus 12 sine 45 into 13 equals to 0. From this equation we will get VD equals to 32.56 kilonewton. Next is summation Fy equal to 0. So we have to take upward positive, all the vertical, that is upward and downward loads we have to mention. So see what we have, first of all VA, as because it is upward, so plus VA. Then we have this downward UDL, that is minus 8 into 5, see, minus 8 into 5. Then we have this 20 sine 60, so minus, as because it is downward. Then this VD upward, so plus VD. Then this 12 sine 45 is downward, so minus 12 sine 45. There is no other load present over here, so moment we don't have to take in vertical loads. So VA we will get as 33.25 kilonewton. Okay, upward arrow. Then to find out Fx, see, there is now here there is a horizontal load present at support A, because there are two inclined loads. So first of all, this is, see, what notations we are taking is right positive. So HA already we have assumed it as right, so we will take plus HA. Then this is going left side, so minus 20 cos 60, and this is going right, so plus 12 cos 45. When we do calculations, you will get HA equals to 1.52 kilonewton. Now first we have to do shear force calculations. So draw shear force diagram. Now see, we have mentioned over here, from while going left to right you have to take upward positive and downward negative. If you are going from right to left, then it is exactly vice versa, that is upward negative and downward positive, but normally we will follow this conventions. Okay, so first of all, let's see what is the shear force at A. This is nothing but VA, that is 33.25. so we will draw a straight line of 33.25. From A to B there is a UDL, so obviously this line will be inclined, and the value we will calculate as 33.25 minus, because it is UDL, 8 into 5, so we will get an answer as minus 6.75, and as because it is minus, so we will draw it downwards. Now from B to C there is no load, so we'll just draw a straight line. As soon as we reach this point C, there is a downward load of 20 sine 60. So what we will do, see, C left and right both we have to write down. So C left, same load you have to copy, and at C from here to here there is no load, but as soon as you reach point, so this is crossing the point, so at point C right, minus 20 sine 60 you'll do, so you'll get answer as minus 24.07. Now from C to D there is no load, so we will draw a straight line, that is D left. As soon as you reach point D, there is a vertical load, that is VD, whatever the value of VD that we have to add or subtract. So see, minus 24.07, it is at D left point, and at D right point the value of VD we will add, and we will get D right shear force. Then again at E left, same value, that is 8.49 what we have received. We will just draw a straight line as there is no load in between, and as soon as we reach this point, we will subtract, not add, because it is downward. That is 12 sin 45, and we will get answer as equal to 0. Now when you draw this shear force diagram, you see there is a change in, like from positive to negative, there is a change in curvature of shear force diagram. This point is called as point of contraflexion, or point of inflection, or point of zero shear. Many times the bending moment over here will be 0, except in some cases. Okay, so we have to first of all find out this distance x. So to find out this distance x, what we will do, we have to just use the similarity of triangle properties which one studies in their school life, that is height upon base equal to height upon base. So height of first triangle, this triangle is 33.25, and let's say we'll assume this length as x. So 33.25 upon x, see we have written over here, equal to, this height is 6.75, so 6.75 upon, if total is 5 and if this is x, obviously this will be 5 minus x, so upon 5 minus x, and we will get answer of x is equal to 4.16, that we can solve on calculator. Okay, now we have to draw a bending moment diagram. So to do this bending moment calculations, first of all we have to do to draw this bending moment diagram, we have to do bending moment calculations. See, at A and B, this both points, the moment will be 0. Now from here to here, that is from like that, at that point x, whatever, see at a moment A, bending moment at A equal to 0, then at x, what is the value? So see, this 33.25, that is VA, into the distance. What is the distance? We have found out 4.16. See, we are finding at this point, so 4.16. Then is there any other load? Yes, there is a UDL, that is 8. So minus 8 into 4.16 square upon 2, that is the formula over here is WL square by 2, as because it is a UDL. So we will get value as 69.1 kilonewton dot meters. Okay. So this bending moment at B we have to calculate. So for bending moment at B, what we will do? See, from again you have to start from here to, like from starting point. So VA, that is 33.25 into 5 minus 8 into 5 square upon 2, this is 5, so because of UDS, so the answer we will get as 66.25 kilonewton meters. Again I am mentioning that how to calculate support reactions of UDL, UVL, point load, everything we have explained in our video, and the link of that video I will give in the description. Okay, now we have to calculate bending moment at C left point, because see, when you have to do shear force diagram and bending moment diagram, left side and right side forces or moments, whenever there is a change in force, you have to find out shear force at left and right side both for SFD, and whenever there is a moment present at C, now here in this case there are two moments present at C and D, so you have to find out bending moment at C left, C right, and then D left, D right also. So about C left we will find out first. So see, 33.25, that is this force, into the length is 7, then this UDL, that is minus 8 into 5. So see, this UDL is not up to point C, so what we will do, we will divide this length 5 upon 2 and we will add this 2. So that is what we have written. See, minus 8 into 5 into 5 by 2 plus 2, and then the answer will be 52.75 kilonewton meters. And when we cross this point, we come across this moment anti-clockwise minus 10, that is anti-clockwise moment, so value is minus 10, so we will subtract this 10 from here and we will get value as 52.75 kilonewton meters. Okay, now next is we have to find out bending moment at point D left. So see, it will be VA into this length, that is 5 into 2 into 3, 5 plus 2 plus 3, that is 5 plus 2 is 7 plus 3 10, so 33.25 plus 10. Okay, see, this is 33.25 into 10, then see this UDL, that is again same way, same concept will apply, minus 8 into 5 into 5 by 2 for this UDL का length, and then 5 by 2 for this UDL's length, and then 2 plus 3 5. So 5 by 2 plus 5, that is what we will see. It is here 5 by 2 plus 5. Then this anti-clockwise moment, so minus 10. So that is what we have written, minus 10 over here. Now this load, that is minus 20, as because it is 20 sin 60 is downward anti-clockwise, so minus 20 sin 60 into the length, this is 3 meters. So see, into 3, and we will get answer as minus 29.46 kilonewton dot meters. Now when we cross this point, that is point D, we come across this moment clockwise 4, so we will add it, so plus 4, and we will get answer as minus 25.46. and at point E, that is the end point, so here the moment is 0. Okay, and this is how we will just plot this bending moment diagram by whatever values what we have received. But from A to B, this is parabolic curve in nature because this is a UDL. So we will just show these lines and we'll just show P as I have said earlier. And this is my bending moment diagram. So clockwise positive in kilonewton meters, and earlier we have drawn shear force diagram, upward positive in kilonewtons. Okay, now last thing remaining is axial force diagram. Okay, now if you see, before drawing axial force diagram, again bending moment diagram also, as we have received, as we have got in shear force diagram, the point of counterflexure, same point of counterflexure we have got here also. Earlier we have given this length as x, so let's say this length is, let's say this length is z, and this total was 3. See here it is 3, so we will say this is 3 minus z. Again we will use the same similarity of triangles, that is 42.75 for this upon 3 minus z equal to this z upon this total length is 29.46. so what we will get, so this is what we get, 29.46 upon z equal to 42.75 upon 3 minus z. So the point of the value of z we will get as 1.22 meters after solving this particular type of equation. Now to find out to do axial force calculations, we are taking left positive and right negative, that is tension positive we are taking and compression negative obviously. So if we see at this point A, see this is right, so 1.52 negative, so we'll draw negative 1.52. Now from A to up to this point C, there is no horizontal load, so we'll draw a straight line. Then as soon as we reach this point C, see we have this 20 cos 60 load, so we will add it. So minus 1.52 plus 20 cos 60 we will get as plus 8.48 kilonewton. So we will draw like from minus 1.52 we will go to plus 8.48. From here till point end point E, we don't have any horizontal load, so we draw a straight line. Now as soon as we reach point E, we are getting this 12 cos 45 load as right side. So see, for this right side load, what we will do, obviously we have to subtract it, so we will get 8.48 minus 12 cos 45. Approximately you will get value like 0 point some digits, but it will be approximately 0, or you get in your calculator 1 point something or 2 point something into 10 raised to minus 3, that is 0 point some digits. So that value is approximately 0 only, so you have to take 0 only, because we are not doing exact calculation on calculator, like we miss some digits while doing calculation. If you take exact digits, then you will get approximate 0 answer. Okay, so the value is 0. So we will draw this line downwards, and this is what about overhang beam shear force diagram, bending moment diagram, and axial force diagram, and with the calculations. Okay, now our next type of question is beam with internal hinges. Okay, so let's see the question. See, this is the type of beam I have taken, wherein from A to B there is a UVL of intensity 20 kilonewton per meters. The length is 2 meter over here. From B to C there is no load, the length is 2 meters. Then at point C we have a roller support. Again here also there was a roller support, I did not mention that at point A. Then at point C we have 30 kilonewton load inclined at 45 degree with the horizontal. Then from C to D the length is 3 meters and we have a UDL of 10 kilonewton per meters. At point D this is the internal hinge, and also the point B was internal hinge. Then from D to E the length is 1.5 meters. At point E we have a fixed support. So the unknowns will be HE, the horizontal load, VE, vertical load, and moment ME. Now this inclined load I have resolved directly over here, that is 30 kilonewtons. I have resolved as 30 cos 45 and 30 sin 45. This sign indicates there is a continuation. So this part only I have drawn over here. Okay, let's just have a look at this. See. Okay. Now first of all we will calculate the support reactions. So to calculate support reaction we will take summation Fx equal to 0, that is horizontal loads, and right positive. So what is the first right positive load I have is 30 cos 45, this load. Okay, so 30 cos 45 I am taking right positive, minus HE, because this I have taken left side, equal to 0, and I would get my value of HE as 21.21 kilonewton left arrow. Whatever I have assumed, my direction is correct. Now second equilibrium condition, I'll take summation moment at B left equal to 0, clockwise positive. I'll just take left part of beam up to point B. So what all loads we have is, first of all we have this load VA, so VA into 2, then we have a UVL, so half into base into height, so half into base is 2, height is 20, into, as we have mentioned in that video wherein we have explained all the types of load calculations and all, so from right angle the length is 1/3. So from here it is 1/3. If I would have calculated from here, then it will be 2/3. So 1/3 into the length is 2. I will get my value of VA. Then summation moment at D left equal to 0. If I take, see, up to D, what all things I have, what all load, whatever type of load I have to take those. So first of all is VA. So VA into 7, 2 plus 2, 4 plus 3, 7. Then I have UVL, so this is half into 2 into 20 for this UVL. Then 1/3 of 2 for this up to this A to B, and then from B to D the length is 2 plus 3, 5 meters. So plus 5. Then I have load this, that is downward load, as we have resolved it. So minus 30 sin 45. See, minus 30 sin 45 into the length is 3 meters, so into 3. Then for this UDL it is minus 10 into 3 into 3 by 2, so 3 square by 2 equal to 0. One more load we have, that is VC, and going clockwise, so VC into 3, and then we will take equal to 0. So we will get our value of VC as 58.43 kilonewtons. Okay, now so by solving this we will get value of VC as 58.43 kilonewton, upward arrow. Now our next type of, next equilibrium condition is summation Fy equal to 0, upward positive. So we will take all the upward loads, upward and downward loads both. So let's see. So first of all we have this VA, that is 6.67. Then we have UVL, but it is downward, so half into 2 into 20 in minus sign. Then we have this 30 sin 45, again minus. Then we have this UDL minus 10 into 2, but it is downward, so minus. Plus VE we have, see this plus VE we have. Then we have VC, that is value is 58.43, this VC we also have. Okay, and equal to 0 when we do, we will get value of V as 6.11 kilonewtons. Okay, now see, one more condition we have to do, that is summation moment at D right equal to 0. So whatever is there on the right hand side of D, we will take that moment as 0. So first we have as ME, as it goes it is clockwise, so ME positive, then minus 6.11 for this VE. So as because it is going anti-clockwise, so minus 6.11 into distance is 1.5 equal to 0. So we'll get value of ME as 9.17 kilonewton dot meters, and with the clockwise arrow whatever we have assumed is correct. Okay, now next part is to do shear force calculations. So at point A, if you see, the shear force is VA, the value is 6.67. so we'll draw a vertical line. Okay, so let's see at point A value is 6.67. now next is point B. So at point B the value will be VA, that is 6.67 what we had, and then minus this UVL, that is half into base into height, half into 20 into half into 2 into 20. So see, so 6.67 minus half into 2 into 20, you will get minus 33.33. Now before reaching this point C, we don't have any load in between, so at C left value will be as same as what we had. As soon as we reach this point C, we get this like see 30 sine 45 load. So and as you go it is downward, so minus 30 sine 45. So C left value is same, minus 13.33, and then it is minus 13.33 plus 58.43 minus 30 sine 45. That is for there are two loads, that is first is VC and another is 30 sine 45, and we'll get this value as we will get the value as 23.89 kilonewton. Now at point D we have to calculate, which is you have to just subtract this UDL, that is minus 10 into 3, which is the value would be then minus 6.11. Then up to before we reach this point E, there's same load, so you have to just copy the same value, and as soon as we this point E, we are getting VE, so we have to just add that VE, and the value what we will get is, see, earlier it was minus 6.11, we have to just copy it, and plus 6.11, that is the value for VE, and we'll get a value as equal to 0. Okay, now in this shear force diagram again we are getting this point of contact flexure, but here there is no triangle, this is the parabolic curvature. So there is another method to find it out, and see at this point there is a triangle, so this we can do by similarity of triangles. This length we have assumed as x, total is 2, so this will be 2 minus x. Similarly this we have assumed as z, total is 3, so this will be 3 minus z, and we have just given names as O1, O2. First of all we have to draw this shear force diagram so that we will get this point of contact flexures. Now we'll just find out this 2 point of contact flexures. So second one we can do simply by similarity of triangles, and the value we will get as 0.61. and for the first one what we will do, see, first of all we will consider this length. Let's say this length is y, so this we will first calculate what is y in terms of x. We have to first find out this value of y, so it will be by similarity of triangles, height by base, that is 20 by 2 equal to y by this x. So we'll get y value as, see, 20 by 2 is y by x, we will get y value as 10x. Now we'll find out shear force at point O1, which is 6.67, that is VA, minus half into, for this UV, half into base what we have assumed as x, and the height was y, so that y we have found out as 10x, and we will equate it to 0, so we will get value of x as 1.16 meters. Now the thing which is remaining is bending moment calculation and axial force calculations. So first of all let's do bending moment calculation. As because the point A, it is a hinge support, so moment at A will be 0. Now at point B, see, we have taken clockwise moments positive from left to right. Now at point B, at this point B, see what all things we have. First of all we have this VA into 2, whatever the value of VA we will put, and we have this UVL, that is half into base into height into the distance. As I have said earlier, distance will be 1/3 of 2, so see 6.67, that is VA into 2 minus half into 2 into 20 into 1/3 of 2, approximately we will get value as 0. You don't even have to calculate this value because B is a internal hinge. Now at point C, again it is same, see, VA into this 4, then half into base into height we have to do for this triangle, that is half into 2 into 20 into 1/3 of 2, and we will add this 2 meter length. Is there anything we have? No, right? So we will find out this value. See, 6.67 into 4, that is VA into 4 minus half into 2 into 20 into 1/3 of 2, and that 2 meter we have added, so we get this value as minus 26.65 kilonewton meters. Now for this O1 and O2 also we have to find out the moments. O1 and O2, the length of x and z we have found out, same, 6.67 into 1.16, that is our length of x. See, up to this moment we have to calculate, so see, VA into this length and then half into base into height into this particular length, that is 1/3 of this length whatever we have found out 1.16. See, so that is what we have to do, like 6.67 into 1.16 minus half into 1.16 into what we will do, 10 into 1.16, that is for y. Earlier, see here, this half into 2 into 20 we have done, but then here if you see previous moment what we had is we had this total UVL, so this total height was 20, but for this we have just this much span. So particularly we have to find out this y value what we had found out earlier, that is 10x. So 10 into 1.16 we will do into what we will do, 1/3 of this 1.16, and the value what we will get is see 6.67 into 1.16 minus half into 1.16 into 10 into 1.16 into 1/3 of 1.16, the value we will get as 5.14 kilonewton meters. Now for point O2, what we will do, see what we have for this point O2, we will just calculate from right hand side. It will be better to, it will be easier to find it out. Okay, if you calculate from left hand side also, it will be same value. So 6.11 is the value of VE. Into this distance we will take this 1.5 plus 0.61, then we have this moment of ME, whatever the value that we will add, and that's it. That's two loads we have. So see what is 6.11 into 1.5 plus 0.61 minus 9.17, that is for ME we had, and then what we have is for UDL, that is minus 10 into 0.61 square upon 2. See, we have this smaller span, right? So in this smaller span there is this UDL, so it is minus 10 into 0.61 square upon 2, and the value what we will get is 1.86 kilonewton meters. Now similarly, when we calculate this like the bending moment at point D, it will be again 6.11, that is V into 1.5 minus we have this minus 9.17, that is the moment of ME, and we get a value of approximately 0. Even this also you don't have to calculate because D is the internal hinge, and at point E, that is bending moment at E, we will get as minus 9.17 because it is a value of moment of ME, and as because it is anti-clockwise, like we are going, sorry, as because it is a clockwise and we are going from right to left, so it will take us minus 9.17 kilonewton meters. Now in between, if you see in this particular BMD, we have got this point of contraflexion, we have denoted it as O3. So we have to just find out what is the exact length that we have got. Okay, so now what we will do is we have assumed this length as A. See what is the exactly, I'll show you. This length we have assumed as A, so VE into A we will do. Then what else we have this moment, so that we will add up, and one more thing we have is this UDL. So those things we will add. See what we get is, it is 6.11 into A, that is for VE, then we have this moment minus 9.17, then we have UDL minus 10 into the length will be like, see we want just this length, and total is A, this length is 1.5, so this much length will be A minus 1.5 square upon 2 we have to do for UDL. So the final answer what we will get is, it will be, we have to just equate it to 0, and then thereafter, see when you solve this equation you get two values of this A, out of which one will be valid because A cannot be 1.5, so you get as A equal to 2.72 meters. Okay, because see this is, after that what we have to do is axial force calculations. We are taking left positive and right, I mean left horizontal load we are taking positive, and right horizontal load we are taking negative when we are going from left to right. So now let's see the diagram. See, and from A till C there is no load, so at this all points it will be 0. Once you reach this point C, we have this inclined load for which we have resolved it, 30 cos 45, the value is 21.21, and as because it's right, so we are taking minus. From here to here there is no load again, so we'll draw a straight line. It is again 21.21 over here, I have not mentioned here. Then from here, when we get this 21.21 value of HE again, we will add it up and we will get value as 0. See the calculations. See, first of all have a look at whole diagram. This is my beam, this is my shear force diagram, this is my bending moment diagram, and this is my axial force diagram. Okay, So see, these are my calculations from A, B. The moments, the value of axial force was 0. At C, the value was minus 30 cos 45, that is minus 21.21. Again at D and E left also it was same, and for E right we have just added the value of HE and we are getting value equals to 0. Okay, this is all about our beam with internal hinge. Now see, the question says figure shows shear force diagram for a beam which rests on two supports, one being at left hand end, and the loads are in kilonewton and distances are in meters. Deduce directly from the shear force diagram. So in this question they have given you shear force diagram already, and what you have to find out is loading on the beam, bending moments at 2 meter intervals along the beam, then every 2 meter intervals you have to find out bending moment, then position of the second support, where exactly the second support is, then bending moment diagram BMD, indicate maximum value of the bending moment, that is PM max, and indicate point of contact fracture if any. Like if there is a point of contact fracture or a point of inflection, you have to mention it. And this is the point, this is the kind of diagram they have been provided to you. Okay, see, A, B, C, D, 10, 5.5, minus 1.5, minus 9, 3, 3, 0. Here also it is 0. The length is 6 meter, 10 meter and 2 meter. Okay, so now let's see the solution of the question, what exactly you have to do. See, I have redrawn this diagram again over here, and let's see the solution. First step is loading calculation. So from D towards A, if we go, shear force is 3 and it is positive. So what we can see, it is from left to right, so point load will be downward, as because it is positive, so the point load will be downward, so that is 3 we will draw over here. Now at point C, if you see this, see the load is from 3 to 9, so it is exactly changing, so you have to just add those, that is 3 plus 9, it is 12. So as because it is negative, so from right to left if you go, negative is upward, so that is 12 kilonewton upward load you have to draw over here. Then between C and B, if you see, SFD is a, see, between C and B, if you see, SFD is a straight line, so obviously there is a possibility of UDL, and it's because it is a inclined line. So now the value of that UDL, it will be, see, what are the exact values? See, you have to just subtract those two, that is 9 and 1.5. This is 1.5, so 9 and 1.5, when you subtract, you get it as 7.5, and the length is 10 meters, so 7.5 upon 10 you get value as 0.75 kilonewton per meter. Slope is positive, so UDL will act downward, so we'll draw a downward UDL, I mean the UDL is like downward, this, so this is the kind of UDL what we get. Now at point B, shear force at B left is positive. See, it is shear force at B left, if you see, it is positive, and load will be, we have to just add those two loads which are 5.5 and 1.5, so those values what we get will be 7.5 kilonewton downwards. See, that is what we will draw over here. Now next part is between B and A, the SFD is a straight inclined line, so there is a UDL, and again same way we will find out this, we just subtract those two, and the length was 6 meters, so see, 10 minus 5.5.6 we will get value as 0.75 kilonewton per meter, and slope is positive, so UDL would again act downward. At point A, if you see, the A right shear force is positive, so the value will be as same as this 10. This is all about our drawing beam. See, just have a look at the whole beam. Okay, now we have to find out all the values of these moments. So first of all we will locate the second support. Now from the load diagram, the second support is located at C, 16 meters from the left support. We can see clearly it is 16 meters. Okay, third step is bending moment calculations at every 2 meter interval from D towards A. So first of all at 0 meter, from D to A we have to go. At 0 meter it will be 0. At 2 meter, if you see, this is minus 3 into 2, that is minus 6 kilonewton. It's I've written plus, sorry, it is like minus 6 kilonewton meter, then at 4 meters it will be minus 3 into 4, like at 4 meter, plus if you see at 4 meter it will be 12 into 2. Then again for UDL, from like after 2 meter it starts with 0.75 square, 0.75 sorry, into 2 square upon 2, as because it's downward, so minus, so this is the value what you get. Then you have to just change this length, 6 meter, then 8 meters, 10 meters, 12 meters. At 14 meter, if you see at 14 meter what you are getting exactly is, see, bending moment at 14 meter, like you will change this, but you have one more load, that is minus 7 into 2, which will be, see, this is 10 plus 2, 12, and after that you will get this again a load, so this is minus 7. See what is the value what we have got. So minus 7 into 2, 1 second. See, we have this one more load also which we have written over here, that is shear force at B left is positive, it is 5.5 plus 1.5, that is 7 kilonewton. So as soon as you reach this point you have to consider this 7 also, so that is what we have considered over here, minus 7 into 2, and after that minus 7 into 4, and at 18 meter obviously it will be 0. So out of this all, the maximum will be 46.5 kilonewton dot meter square. And then after like getting all these moments, you have to draw this diagram also. Okay, so this is what about your diagram. Now remaining part is location of point of contact fracture. So in BMD, O lies between B and C. Let's see, this is what the point of contact fracture we have got. Okay, so now in BMD, O lies between B and C. Let it be at a distance x from support C. So this distance we have given as x. Now to find out depth, what we will do is we will take bending moment at O equal to like whatever the value you will get, and we will equate it to 0. So first of all we have minus 3 into 2 plus 6. See how? So this is minus 3 as going it is clockwise, so right to left clockwise is negative, so minus 3 into this 2 plus x. Then what we have this load, that is plus 12 into x, and we have this UDL, that is minus 0.75 into x square by 2. So this is what we have, as I have said just now, and we'll equate it to 0. So we'll get two values of x, out of which we have to select proper value, that is 0.69 meters, and we will show it over here like this. Just have a look. Okay, now the last topic from SFDBMD, which is frequently been asked in exam and which is important also, is relation between loading, intensity, shear force and bending moment. So this is the kind of beam carrying general loading we have drawn. We have taken this section MMNN, distance is dx. Let's say this is A and B supports, and this is the kind of beam what we have, out of which we have selected this portion. Let's say there is a UDL, this is W dx, as because this is dx. Then this like the shear force we will take V plus dV, and this is V. This moment we will take M plus dm, this is M, and this intensity is W, which is beam element of length dx. So figure A shows a beam carrying general loading. Consider an element of the beam formed by taking two cutting sections mm and nn, these two, distance dx apart. This distance dx, this is just an assumption. The general loading over the element can be assumed to be an UDL of intensity W per unit run, since dx is very small. On the right face of the element, the shear resistance V and moment resistance M is developed, this one. Okay, now on the left face, shear resistance force has increment of dV like this and becomes V plus dV, while the moment resistance M increases by dm and becomes M plus dm, like this one. Okay, like this too. So now about this too, since the beam is in equilibrium, an element of the beam must also be in equilibrium. So applying COE, that is condition of equilibrium, to the element, we will take summation Fy equal to 0. So as because V plus dV is, we are taking upward positive, so V plus dV is positive upward, minus V downward, minus W into dx for UDL equal to 0. we'll get value of dv as w dx. So dv by dx equal to w, we denote it as equation number 1. So equation 1 implies that the rate of change of shear force at any section represents the rate of loading at that section. Now if you take summation moment equal to 0 and clockwise positive, so we can see minus m plus dm, as because it is anti-clockwise we are taking clockwise positive, plus we have m, plus we have v dx for this, as because it is clockwise we are taking at this particular point 0, plus we have w into dx square, as because it is a ureal, upon 2 equal to 0. So after doing this rearrangement, like calculations, we will get minus dm plus v dx plus w into dx square by 2 equal to 0. The square of small quantity can be neglected, like this dx is very small of larger x, so dm we can say is equal to v dx. So you can say simply dm by dx equal to v, equation number 2. So equation 2 implies that the rate of change of bending moment at any section represents the shear force at that section. So this is all about this topic: shear force diagram, bending moment diagram, and axial force diagram. Now after this we will start with the exact uses or real life applications of whatever the topic, like this topic is SFD, BMD and AFD we are studying. Now before starting with that, please do like, share and subscribe to our YouTube channel. Also press the bell icon so that it will be most useful for you to get the notification of our upcoming videos. Mention whatever the comments you have in a comment box and share it among with your friends. Now whoever is interested, we can continue with the further session, that is for the applications. Now let's start with what are the exact uses or real life applications of the SFD, BMD and AFD. Now the question comes in mind, why one needs to study this, like why one needs to understand how to draw SFD, BMD and AFD, that is shear force diagram, bending moment diagram and axial force diagram. Before that, first understand shear force is the vertical, that is upward and downward force. Bending moment is clockwise or anti-clockwise moment, and axial force is horizontal, going left or going right force, that is going towards or going away force, which shows tension either or compression. So see this, what it says is, why I find the shear force diagram and bending moment diagram of a beam or column, and what is the uses of SFD and BMD in the field. Okay, so what we will see, SFD, BMD, AFD are merely tools to a greater purpose. Shear force diagram SFD and bending moment diagram BMD form the basis for design of beams in general. Axial force diagrams come additionally for column design. The column is nothing but a vertical structural member in any building or any whatever the structure is getting constructed, and the beam is the horizontal member which transfers the load to the column. So understanding these forces conceptually is the key to understanding their use in the design and field. Now any static structure which is subjected to loading will develop internal stresses to prevent deformation, much like the immunity of the body resists the impact of changes in environment and stimuli. Let us look at the structures separately. First of all, we can see this beam. It is a simply supported, one end is hinged, other end is roller, and it has loads P1, P2, P3 and P4, and one more is there P5. In between P3 and P4 there is a UDL of intensity W. So this is the beam. See, this is the beam. We have taken a section XX like between loads P1 and P2. Okay, and see this is kind of FBD at section XX. See, I'll just zoom it. At section XX we will get this FBD. See this, there will be a downward load, S shear force, A axial force generally absent, and we have this moment M bending moment. See, this will be like, what it shows is loading is in lateral y direction. This is y axis, this is x axis. Okay, now zoom out. Assumption: loading is lateral in direction. The beam will be subjected to probable deformation along the lateral y direction and also rotation. There will be no axial, that is longitudinal, internal stress generation, as there is, or generally you can say, no external loading in this direction. Now the deformation along y direction will be resisted by an internal stress generated in that direction. This stress is usually called shear. The total value of shear stress at any cross section is called the shear force at that point, that is at that cross section. A diagram depicting the shear force values at each point of the beam is plotted to form a diagram known as shear force diagram. You can denote it as SFD. Similarly, to prevent rotation of the body, each point develops some kind to internal moment resistance. This internal resistance of the body at any point is known as bending moment at that point. The diagram depicting the bending moment values at each point is plotted to form bending moment diagram, that is BMD. Now, when we talk about columns, the above two internal forces may be generated. However, the primary form of loading in columns is in an axial direction, that is longitudinal. As such, the internal stress generated will be axial in nature. This stress is known as axial stress. The total value of axial stress at any cross section is called the axial force at that point or cross section. The diagram plotted for each point along the length is known as axial force diagram, that is AFD. Now, use of these diagrams. Every structure will try to resist the deformation by developing the above internal resistance, that is shear moment and or bending moment. However, the properties of the body will decide how much resistance would be provided against loading. For example, a beam of concrete material has very high resistance to shear. It is, however, very weak in tension. Then a steel beam has high resistance in both shear as well as bending. However, it is very expensive when compared to concrete. Hence, while designing a beam of concrete, we find the points of maximum SFD and BMD values. These values in turn give us the idea as to the kind of material and geometry we need to provide to resist deformation or failure in general. Since concrete is very cheap, we try to provide as much of it as possible. However, it is weak in tension. So you can just note down this diagram. See, this is the kind of diagram, and these are all the zone of maximum shear force for design, and these are maximum bending moment for design. Okay, these are the kind of diagrams. Now zoom out. Hence, for zones of maximum bending moment which we find from BMD, we provide steel reinforcements. We also find zones of maximum shear force from SFD. If the shear force values surpass the concrete's capacity resistance, we provide steel shear stirrups in order to resist the additional shear. Same concept is applicable for columns as well. As you can see, SFD, BMD, AFD are merely tools to a greater purpose. The values from these diagrams helps us decide the material and geometry of the design elements. Now, shear force and bending moment diagram are the next consecutive steps of a loading diagram. SFD, it helps you to understand the shear forces, and BMD helps you to understand the bending moments on a structure. Now, what are the exact applications? While working on complex structure where civil engineering thumb rules, basic considerations of depth and span from experience of civil engineers does not work well, you need to double check for failure and safe structure. Then these basic rules come to your help. Of course, you can use it on field, because on execution, that is exact what we are going to do, you can find it with help of just a paper and pen if you are familiar with the diagrams and loads working principle. So this is all about real life uses or exact application of shear force diagram, SFD, bending moment diagram, BMD, and axial force diagram, AFD. Here the topic ends. Now, if you like the content of the video, please do like, share and subscribe to our channel, and also press the bell icon so that you'll get a notification of all our upcoming videos. If you have any queries, any suggestions, please mention in the comment box. And for this, whatever the things we are explaining now, we'll be giving in description, we'll be giving links of both the files of the numericals what we have solved, and of this particular applications we'll also mention a document file, so you can just visit this file of Google Drive. So stay tuned with our video and share it with your friends and your colleagues as well. Thank you so much for watching. Bye, see you in the next video.